This is 7.1.2 least squares. In this subsection, we'll introduce the least squares problem. The problem at hand is still ax equals to b, and we are given a, and we are given b, and the problem is to find x. In the last lecture, we talked about consistent equation, where if b is in the column space of a, then we can find x such that ax will be equals to b, and therefore there is zero error in approximating x. Approximating x using b. We also talk about the situation of inconsistent system of equations. Typically, we said that when the number of equations, the number of rows in A is greater than the number of variables n, then there might be chances that there are inconsistent equations. Specifically, that is, B is not in the column space of A. In other words, we cannot form B using any linear combinations of A. That is, no matter how we find x to perform the linear combinations, ax will never be equals to b. So what should we do when given such a situation? The idea is that we have to find x such that ax will produce a b hat, and b hat is as close to b as possible. Let us call the best x that does the trick x hat. What happened is that now we want to find x hat such that ax hat is as close to b as possible. By as close, we are talking about the Euclidean norm of the approximation error. This two parallel bar is the symbol for norm. What we are saying is, let's find x hat such that compared to any x, the error on the left will be the best, as in the smallest we can ever achieve. This is called the least square solution. Here, the word least square means that it is actually the square root of a sum of square, because we're talking about the norm. The norm is the square root of a sum of squares, and here is the approximation error. The approximation error between b, the one vector we are desiring, or it is the target, to ax hat, that is the one we are producing. We have actually seen this problem before under dot product, under orthogonal projection, as well as in Gram-Schmidt. What we are saying is that we have the columns of A, and the shaded region is the column space of A. We can produce any vector ax in this point or ax in this point by finding different combinations of A, since if this is A1, A2, A and n columns, and by using different x1, x2 and xn, we are actually generating x1 a1 plus x2 a2 plus xn an, finding different columns of A, or scaling different columns of A to get ax. The lecture in orthogonal projection tells us that if we want to find the smallest Euclidean norm of the approximation error, because this is B, our desired output, and this is A hat, maybe I should call this B hat, our best approximation to B, the smallest error, E, smallest, is the norm of E is the norm of B minus B hat, which is equals to B minus A hat, AX hat. And by orthogonal projection, we remember that E, the error, is orthogonal to the column space of A. Of course, in the situation when B lies in the column space of A, then B would be inside or on one of the point of the column space, and there will be no error. That situation will only happen when AX equals to B is consistent. And when AX equals to B is inconsistent, B does not lie on the column space of A, and you see in this diagram, it is not on the blue plane. Some standard terminology, this is the error vector, we call it E, and it is point B minus AX. And each of these terms, E1, E2 until EM, will be the error at each coordinate. And here, we are interested in least squares. The word squares here means the error square. So it is the norm of the error square. Using dot product, remember, since norm of E is equals to square root of E dot product with E, therefore norm of E square is equals to E dot E. And referring to your dot product equation, E dot E is equals to individual element square. The number of elements in vector E is M element because matrix A belongs to Rm by n. Number of equations is M.